Hey everyone, welcome to this week's video. The topic is thermal analysis, and specifically we are going to be looking at how to set up the thermal analysis simulations using the Solidworks for a bimetallic strip problem. Okay, so to begin with, let's take a look at the direct analogies between the structural simulation and the thermal simulation and what are the similarities in between the two. So the displacement in the structural simulation is equivalent to the temperature in the thermal simulation. Okay, similarly, the strain that we measure in the structural simulation can be compared with the temperature gradient, Kelvin per meter, in the thermal simulations. Stresses induced in the structural simulations are compared with the heat flux, which is given in terms of the watts per meter square, and the load or the external disturbance parameter is equivalent to the heat source in the thermal simulation. So there are direct analogies between the structural and the thermal simulations, and the similar set of equations can be formulated for thermal studies as we have done it for the structural simulation studies using the direct formulation method. Okay, so let's take a look at the problem on the bimetallic strip, and what we're gonna do here is to find out the deflection of the bimetallic strip because of the presence of the high temperature in the environment. Okay, so bimetallic strip is a commonly used equipment or device to measure the temperatures, and what it consists of is two dissimilar metals bonded to one another, and in this case we are bonding the copper and the alloy steel with one another, with the copper material on the top and the alloy steel is on the bottom, as you can see in this photo here. The idea is that once they are bonded and the temperature is increased, obviously both these metals have different coefficients of thermal expansion, and due to that there will be an uneven expansion in these two metals, and because of the uneven expansion, and since they are bonded with one another, the strip is going to curve, and so the deflection can be measured because of this thermal load that's causing the deflection. Okay, so that's the basic idea here, and the dimensions which we know here are 500 millimeters length, 40 millimeters wide, and 10 millimeters thickness of the strip. So these are two identical pieces of metals bonded to one another, and we will simulate that using the simulation. But before we start off with the SolidWorks simulation, let's consider some theoretical aspects of it. So as shown in this figure A, these are the two different strips of the different metals, and if they are unbonded and if you have a temperature difference, then there is going to be the expansion or the strain in the amount of delta epsilon, and this delta epsilon is related with the coefficients of linear expansion and the temperature difference. So one metal is going to get expanded more than the other metal if the coefficient of thermal expansion is higher than the other. So this is when they are unbonded. Okay, but what if you bond them with one another? Then because of this bonding there will be an uneven expansion, and since the surfaces need to be in contact with one another, the one metal will expand more than the other, and so the strip is going to deflect, and so there is going to be a deflection in the amount of delta. So the experimental setup, as you can see here, the bimetallic strip is fixed on one side and they are bonded with one another. let's say the overall span is equal to x units, and in our problem we have considered this as 500 millimeters. Okay, so x equal to 500 millimeters, and once we have the temperature effect, or this is also called as the thermal load. Due to this thermal load, there is the deflection in the strip, and this deflection is given in the amount of delta. Okay, so theoretically this equation is used to find out the curvature. So K is basically the curvature, okay, which is also given as the reciprocal of the radius of that curvature. So if you have, this is the radius r, the center is obviously somewhere down there, but that's the radius, and so 1 over r is given as k. So if I just draw it here, something like this, if this is the deflection of the beam, okay, this is the original position of the beam or the strip, and once it deflects due to that, so let's say there is some center that you can locate it at some point with the radius r, that's the radius r. Alright, so because of this curving of the strip, okay, so you have this radius of that curvature, and k is given as 1 over r, and the value of this k is given as 12 times delta epsilon over h times E star plus 1 over E star plus 14, where E star is the ratios of the two Young's moduli of elasticities of these two metals that we are considering. So E star equals to EA over EB, and delta epsilon is equal to alpha A minus alpha B times delta T. So delta T is the temperature difference. So you're going to have some initial temperature, generally the room temperature, and then the final temperature, or we can also call that as a steady state temperature, which means that initially the strip is present in the normal room temperature, and then we expose it in an environment where we have a constant steady state temperature of, let's say, the initial room temperature is 20 degrees and final temperature is 300 degrees Celsius. So the delta T will be equal to 280 degrees Celsius, and alpha A and alpha B's are the the coefficients of thermal expansions for these two metals. All right. So this is the equation that we can use to calculate the curvature value based on the theoretical equation, and then once we simulate that in the SolidWorks, then we will compare the two to get the validation of the results. So let's see how these values come out to be. So using this equation, k equal to 1 over r, and this equation, so h is given as 10 millimeters, which is the thickness. Okay, so h equals to 10 millimeters, which is equal to 0.01 meter. Alpha A and alpha B are the linear coefficients of thermal expansions of the two metals. So for copper, it's equal to 2.4 times 10 to the negative 5 per degree Celsius, and for steel it's 1.3 times 10 to the negative 5 per degree Celsius. The Young's modulus of elasticities are also presented there, and let's say the initial temperature was 20 degrees Celsius, and the final or the steady state temperature is equal to 300 degrees Celsius. So the temperature difference delta T is equal to 280 degrees Celsius, and if we plug in these values in this equation to find out the value of k, once we plug in these values, we will find that k is equal to 0.225 per meter. Okay, so that is the theoretical calculation that we have, and now let's take a look at the SolidWorks simulation. But in the SolidWorks simulation, what we are going to be doing is getting this value of delta once we set up the simulation, and then use that delta in the equation that we are going to be looking at in the next slide to compare with the curvature value of 0.225 in this case. So when we look at the geometry of this bimetallic strip, what we can see is that the deflected strip, as you can see in this sketch here, where the delta is the deflection, and I'm basically zooming it in this bigger sketch here. So this dark horizontal line is the length of the strip, which is the x millimeters, and once it curves, then we have the delta as the deflection. Okay, so the beam that curves is shown in this arc here, and due to this deflection or due to this curving of this beam, you have the radius of curvature where you can locate the center at some point. So if we create a geometry like this, and then we see the length of the beam here, let's say up to this point, that's the length of the beam x, and that's the deflected part of the beam. So this is the amount delta, and so if we draw a horizontal line, let me name these points as A, B, C, D, and let me say this is the point E. So the relationship, this 1 over r, or the radius 1 over radius of curvature equal to k, that's what we have calculated using the thermal, theoretical equations. This 1 over r equal to k can be given as 2 times sine of tan inverse delta over x over square root of x square plus delta square. Although this equation looks a little complicated, but it's really simple to see how the geometry is formed because of this deflection. So if we consider a triangle ABC, we can see there are some relations that we can form readily, as the length of AC equals to square root of x square plus delta square, because that's the hypotenuse. And from point E, if we draw a perpendicular line on AC, that is going to divide this whole length AC into 2 equal parts of AD and DC, because if AE is R and CE is R, and so this is the arc. Okay, AC is an arc with E as the center point, and if you draw a straight line between A and C, and then you drop a perpendicular from E on that straight line AC, then it will divide this straight line into 2 equal parts. So that's basically the geometry here, and so we can get length AD equals to half of the length x square plus delta square. So once we find the length AD, which is half of the square root of x square plus delta square, now if we look at the angle theta here, okay, so this angle theta for the triangle ABC, we can formulate that in terms of tan. So tan theta equal to length BC over length AB, right? So as per the geometry here, BC over AB, and BC is delta and AB is x. Okay, so we can write down theta as equal to tan inverse of delta over x. All right, so very simple mathematical relations you can form based on the simple geometry that we have. So we have two things here. Now length AD is equal to half of square root of x squared plus delta squared, and the theta can be given as tan inverse of delta over x from this triangle ABC. Now if we see here, this angle BAC is equal to theta, which means this angle EAC is going to be equal to 90 minus theta. Okay, because the angle EAB is equal to 90, and if this is theta, then this has to be 90 minus theta. And if we consider now the triangle AED, so for the triangle AED, the angle ADE is 90, and this is 90 minus theta, so the angle AED is also equal to theta. Okay, again, just by very simple geometry here. Now, so for triangle AED, we can again write using the Pythagoras theorem, in terms of the sine. So sine of theta, so if I write sine of theta equal to the opposite side, which is the length AD, divided by the hypotenuse, and hypotenuse in this case is length AE. Okay, so AD we have already found out. What is that? Half of square root of x square plus delta square, and AE is equal to the radius of curvature. And that's how we can get this equation that we want to be using it to compare for the SolidWorks. So this one now again we can further write it in the final form as let me rewrite that. Sine theta equal to half of square root of x square plus delta square over r. So we can rearrange these terms and write this down as 1 over r equal to, let's take 2 on the other side, so that becomes 2 sine theta divided by square root of x square plus delta square. Okay, and then sine theta, so theta we can write it down as tan inverse delta over x. So this is equal to finally 2 times sine of, in bracket we can write down as tan inverse of delta over x over square root of x square plus delta square. Okay, and 1 over r is equal to k. So that is how the final form of the equation we can get it based on the geometry of this strip deflection, that 1 over r, or that is equal to k, equals to 2 sine tan inverse of delta over x over square root of x square plus delta square. So all we need from this equation to get the value of this k is the value of delta, because x is already known, which is 500 millimeters in this case, and delta is something that we're going to find out from the SolidWorks simulation. Plug it in this equation and then get the value of k that we can compare with the theoretical value. Alright, so let's now go to the SolidWorks simulation. Let's do the simulation and then come back again here to see the value of this k that we can find out from the simulation. Okay, so let's start with the SolidWorks simulation for this problem now. So I'm going to start with the new part file. Let's click OK. Let's use the units of millimeters, and let's sketch on the front plane, I'm going to start sketching on the front plane with the rectangle option. Let's put the dimension for the length, which is 500 millimeters, and for the thickness this is 10 millimeters, and I'm going to extrude this by 40 millimeters to make it a strip. Okay, and what we're going to do is save this, and once you save this you can create another an assembly, let's say part 2. I'm just saving it in the desktop here, and what I'm going to do is make an assembly from this part, place it here, then go to assembly again and insert component. Let's use the same part one more time, so that way we have two parts in this assembly file. And then I'm going to go with the mate option. So the first I'm going to assemble the two side faces, then two right faces, and one last thing I'm going to do is let me see if what are the I think there are 3 of them here. Let me see what's going on in this case. Okay, I'm going to start doing this assembly one more time, and first I'm going to assemble these two faces. Then I will align the parts. Let me try to move this part a little down here, and then use the last mate to finish this assembly. For some reason I'm not able to get this assembly done. Let me try it one more time. This face, this face I want to assemble with that face. There you go. So once you create this assembly and once it's fully defined, then we can start off with the simulation. So let's start a new study. In this case, we don't really need to do the thermal simulation. The static simulation is sufficient to model the static or the steady state temperature analysis for the simulation. So we don't really need to go for the thermal simulation unless we want to do the transient analysis. But for a simple temperature load, we can just stick to the static analysis and then use the temperature external disturbance parameter from the static study itself. So I'm going to click OK with the static study, expand the parts. The first part I will be using as the copper. Click apply, and you can notice that the thermal expansion coefficient here is 2.4 10 to the negative 5. And let's click apply, then click OK. And then the other part what we will be using is the alloy steel, so I'm going to click apply to that. And once we assign the material, I'm going to go to fixtures, click on the fixed geometry. So I'm fixing the geometry on one side, and For the external loads, I'm going to right click on it, and you will see the option that says temperature. Click on the temperature. I'll select the two bodies here for the assigning the temperatures, and I'm going to change the units to Celsius and then put 300 degrees Celsius as the temperature. Click OK. And one last thing we want to do is set the initial temperature. So I'm going to right click on the static part, then properties, flow thermal effects, and here reference temperature at 0 strain, I'm going to change that to 20 degrees Celsius. Alright, so then we can mesh and start the the simulation here. You would notice that it says excessive displacements were calculated in this model, which is expected, and so this becomes a non-linear study. So I'm going to click yes because I want to still continue analyzing this. And once the study is completed, you would double click on the displacement, and as expected the beam or the strip deflects in the downward direction, and the resultant displacement or the maximum displacement at this extreme location, which is expected there, is equal to 29.29 or 29.3 or 29.2 millimeters. That is the deformation here. Okay, so we're going to take 29.2 in our calculations, and then that's basically equal to the value of delta, and we will compare that with the theoretical value. So here we have 29.2, or you can even take 29.3, and x is 500 millimeters. We can plug that in this equation, and once we solve it, we will get the answer as 0.233 per meter, as what we had found out theoretically as 0.225. Okay, so that's basically the theoretical validation of the the equations that we have used with the SolidWorks simulation.